Today we're going to talk about modular arithmetic. Modular arithmetic is like telling the time, so actually you've done it all your life. Modular arithmetic. So, arithmetic. You all know that if you use the 24-hour clock, 13 o'clock is the same as 1 o'clock. So 13 o'clock equals 1 o'clock. Whoops, 1 o'clock. And 14 is the same as 2, and 15 is the same as 3, and so on. And the reason is that 14 and 2 are 12 apart. So when you go around the clock, you go 1, 2, there's a clock, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, and then you get back to 1 again. And then you go around, and every time you get back to 12, you go around to 1 again. So if you wanted to say, if you said something like, you know, if you start at midnight and you go on 8 hours, you get to 8 o'clock, and if you go on another 8 hours, you get to 16 o'clock, and if you go on another 8 hours, you get to 24 o'clock, and 24 is again the same as 0. So now, imagine if we lived somewhere where there were only, say, 5 hours in the day. So we might have the following clock, where we have 1, 2, 3, 4, 5. So we can imagine this being some kind of little clock of some strange description. It's not very well spaced out, is it? So here, every time you get around to 5 o'clock, you go back to the beginning again. And so 5 would be the same as saying 0 o'clock equals 0 o'clock. So you know, usually when we say 0, 0, 0, that's midnight. So here we go, 0, 1, 2, 3, 4, 0, 1, 2, 3, 4, 0, and so on. So you can imagine writing out an addition table. Let's write out an addition table for this case. So we've got 0 o'clock, 1, 2, 3, and 4, but 5 o'clock is the same as 0. Okay. So if we add 0 to everything, nothing happens, of course. If we add 1, we get 1, 2, 3, 4. But if we go from 4 o'clock and we add 1, we get back to 0 o'clock again. So this is going to be 0 here. So now if we do 2 add 0, we get 2, 3, 4. But then here, we've got back to 5, so we get 0. And 2 add 4, so we go to 4, and then we add another 2, goes 1, 2. And we get back to 1. So I hope you can see what pattern this is going to give us. 3, 4. Then 3 add 2 is the same as 0. 3 add 3 is 6, which is also 1. And 3 add 4, we start here and go 1, 2, 3. We get back to 2 again. So then we have 4, 0, 1, 2, 3. So we have this nice kind of swirly pattern coming down here. Like this. Now let's see what happens if we write out a multiplication table on this clock. So we can do multiplication. 0, 1, 2, 3, 4, multiplied by 0, 1, 2, 3, 4. Well, of course, 0 multiplied by anything is still going to be 0. And 1 multiplied by anything is still going to be 1. Now, 2, well, we can put all the zeros down here as well, and 1 multiplied by anything. Did I just say it was still going to be 1? I meant it was going to stay exactly the same. So down here as well, 1 times these things are still going to be those things. So now let's look at something a bit more exciting. 2 2s are 4, fine. 2 3s are 6, but we know that 6 is the same as 1. Right, so we could write in some more things here, saying that this is the same as 6, this is the same as 7, this is the same as 8, this is the same as 9, so this is the same as 10, same as 11, this is the same as 12, this is the same as 13, this is the same as 14, 15, this is the same as 16, 17, 18, 19, 20, wait, that nearly gets us everything. So 2 3s are 6, that's the same as 1. 2 4s are 8, that's the same as 3. 3 3s are 9, that's the same as 4. Oh dear, that was supposed to be 2 3s are 6, that's the same as 1. So we might as well do this symmetrically. 2 4s are 8, that's the same as 3. So now, 3 3s are 9, that's the same as 4. 3 4s are 12, that's the same as 2. So we get a 2 here as well. And 4 4s are 16, that's the same as 1. So this is what a multiplication table looks like. We can check that it's symmetric, so we can draw in some patterns that help us see what's going on. So this is the diagonal here, so everything should be symmetric around it. And it is. So what's happened here? If we concentrate on this thing going round and round, every 5 will come back to the same place, right? So it's easy to see what's going to be the same as 0, because it's going to come back every 5. We'll get 5, 10, 15, 20, 25, 30, 35, 40. Those will all be the same. And going out in this direction, I don't think I need my tables anymore. Let's get rid of this table. And let's get rid of this table. So here, we start 1. What else is going to be the same as 1? Well, if we go around 5, 6 will be the same, 11, 16, 21, 26. So every 5 here will be the same. And then 2, if we add 5, it's 7, 12. So every 5 here will be the same. So all of these are the same. Two numbers come out being the same if their difference is either 5, 10, 15, 20, 25, or so on. So we can define this new form of equivalence on numbers. So here we've said that A, we're going to call it, is congruent to B modulo 5, because we're doing a 5-hour clock. What this means is that the difference between A and B, B minus A, is divisible by 5. And this, we sometimes write as 5 divides B minus A. So that's exactly the relationship we have here going around this clock, right? If the difference between all of these is divisible by 5, it doesn't matter. We don't care how many times it was that we went round. We just want to know that we went round a whole number of times, because then we still always land on this hour. And if we go around a whole number of 5s starting at 2, we'll always land on this hour, and so on. So this is what modular arithmetic is all about. And we can do it for any other numbers of hours of the day that we want. So in general, A is congruent to B modulo n, and we usually abbreviate modulo to mod, means that n divides the difference between B and A. So what we're going to see is that you can do all sorts of arithmetic using modular arithmetic instead of ordinary arithmetic. And it's a bit like only caring about what the remainder is after you've divided by n. So here, all we cared about was what the remainder of this number would be after we divided it by 5. We don't care how many times we went round, we want to care how much was left over after we'd been round a number of times. So we'll talk about that idea more next time.